Hello, everyone. Thank you for joining us for the EVI Women in STEM seminar series. Our guest speaker today is Marie Charpagne, who is currently an Adjunct Assistant Professor at the University of Illinois. Hello, Marie. Thank you so much for joining us today. We really appreciate it.
Hi, Heidi. Thank you.
So today we're really going to try to understand the basics of the topics that Marie specializes in and how they can impact on energy and climate. So first, we're going to talk about some background on the science involved in your research. So although I mentioned it, I'm really interested in what you specialize in, and in layman's terms, what does it mean?
Yeah, so I design new metallic materials and alloys with increased mechanical properties and mechanical performance and tolerance to damage for extreme environments. And so what that means, extreme environments, so that means extreme temperature, very high temperature, very low temperature, extreme loads, so extreme forces applied onto these materials, but also extreme chemical environments. And so the goal of this research is to allow technological shifts, new ways to produce energy, for example, and designing safer and more durable metallic materials for all the structures that are going to go into this new energy generation procedures. Yeah, basically to reach that goal, I have an experimental approach. So that means that I make new alloys, right? I process them, I test them mechanically. So in other words, I expose them to these extreme environments. I pull on them until they break. Sometimes they just stop on the way to check what's going on. But basically, that's the idea, right? So the key to their mechanical performance is encoded within their small scale structures. So this means that I have to look at that scale, which is the scale of basically the human hair and down to the atomic scale, to understand how and why they broke. And so once I know that, I am able to design new chemistries, new alloys that will have better resistance in these extreme environments and therefore extended lifespan.
Okay, and what exactly is an alloy?
So an alloy is a mix of several metallic elements altogether. If we were to look at one isolated pure metal, it would have very poor mechanical properties. But if you mix several, like for example, when we go from iron to steel by adding carbon to iron, we have much better properties. So that's what alloying is for.
What technology are you looking to develop, if any? And how does the science work behind it specifically for the advancements that you want to put into place to help the energy and climate?
Yeah, so in my EVI sponsored project, I seek to design materials that can operate at extremely cold temperatures. We call that cryogenic temperatures. And we're talking about minus 150 C and down. So the main application in terms of energy is hydrogen storage. As far as I'm aware, we currently do not have a simple solution for storage and circulation of hydrogen as a whole. So it's really critical to make this hydrogen industry a reality, to have a supply chain and storage system of some sort. So at room temperature, hydrogen is gaseous, but when you cool it down to a temperature at which it becomes in a liquid state, you save a lot of volume, right? So that's a very promising way of storing hydrogen. But the problem is that we don't have much insight into the material's mechanical behavior or the material's properties and lifetime at these extreme temperatures. So that's what we're looking into.
What is the importance of designing new metallic material for hydrogen transportation?
Right. So I believe there are obvious environmental challenges here. I believe in hydrogen as a renewable energy. Essentially, this idea of cryogenic storage, that's not new. Several other gases are already stored at cryogenic temperatures to ease their transportation. That's exactly the same reason as why we would want to cool down hydrogen. So we can think about current examples are liquid nitrogen, liquefied natural gas that we use to heat up our houses. So to transport it, it is first cooled down, right? These are cooled down to minus 200 C, minus 160 C roughly for liquefied natural gas. And in general, we use stainless steel for storage, like to carry. These are great alloys. They have an outstanding combination of mechanical properties, resistance to harsh environments. And that's why we see them all around us in so many applications. But they were not designed to operate at cryogenic temperature in particular. So they're suitable, but they're not optimized. So the challenge here is to design new materials that will allow us to cool down hydrogen. And to do that, we'll have to go down to minus 250 C, so even lower than what we have to do for liquefied natural gas and others. But surprisingly, we have very limited knowledge about life expectancy of those materials. So our approach is really to explore new chemistries for those alloys and design alloys that are really tailored to the extreme cold so that they have a greater lifespan in those harsh conditions.
So the main goal of your research, if I'm understanding correctly, is to be able to transport hydrogen in a more effective way using alloys so that we can then have a more efficient way of having renewable energy.
Yeah, exactly.
Perfect. And what gaps or barriers are there in your development preventing the technology from going into any certain market?
Yeah, right. So the main challenge I want to say is our very limited insight into the very small scale early damage processes that happen in those materials as we will use them, right? So if you think about how we're gonna load and unload our hydrogen tanks, those materials are gonna be subjected to cycles of loading and unloading. And we have very limited insight into the very fundamental processes of like how the atoms are going to be displaced and changed and what really allows damage to develop in those materials. So once we gain this very fundamental insight, we can learn from that and design new alloys that have like extended lifespan, right? So we can learn from like breaking materials that already exist with this fundamental knowledge, really using that as a leveraging tool to design new materials that will not break in such a way.
Perfect. So it's still definitely the developmental phase.
Oh yeah, for sure. Yes, there is a long way to go before we can allow a hydrogen industry. And I think that's why it's really exciting to be working in that field right now.
In a larger picture, how does this research in the end help combat climate change? Like, what is your ideal application of that research?
Yeah, right. So I think it just goes beyond the hydrogen industry, the way we can nowadays think about designing new materials. So like we've mentioned, enabling this hydrogen industry is really a daunting task, right? So there is still a lot of work, many obstacles to overcome to allow this and make this happen. And my belief is that designing materials with extended longevity, regardless of the end application, can be hydrogen or space exploration, anything. If you can think of your materials, think of designing your materials with a longer lifespan as a mindset, that will not only increase the safety of the installations, in other words, like mitigate the breakage of pipelines and all these circulation structures, but that will also involve replacing parts less often. And in that way, we can save natural resources. So I think it's time for us to approach modern engineering problems with that mindset, that even though we're moving towards renewable energy, the natural resources that will allow us to get those structures all set up, these are not renewable. So we have to really preserve them and design very sustainable and like materials with a long lifespan.
What is the usual turnaround time for an experiment of yours?
So do you mean how long it takes to run an experiment or develop an experiment?
I would say either or, because I know sometimes it depends on what you're working with. Like if you're working with bacteria, it could be a pretty fast experiment, but I was curious to see how long an experiment usually takes.
Right. So develop a new experiment several months, right, to get everything to work nicely. Sometimes when you design a new equipment, you have like air injectors and like vacuum system. There is always a leak. There is always something that was wrong, a part that's missing, something that you could improve. So that takes a lot of patience and dedication. And then in general, I want to say the longest my experiments last when I'm testing my materials, the better it is, right? Because that means that my materials are resisting to the harsh conditions that I impose on them. So when they don't break right away, that makes me happy in a nutshell, really.
Perfect. And what would you and or why would you recommend somebody to study and experiment on this same topic?
So I'm super passionate about what I do. I've been passionate for many, many years, and that has never left me. I just find material science as a whole very intriguing because we learn to link the very small scale processes, so how almost the atoms behave. We learn to link that to macroscopic behavior, so some behavior that we can appreciate at our scale. So I just find this linkage and our ability to establish that linkage very fascinating, and that's why I wanted to dedicate my career to that. But overall, I think now is a really good time to be working in that field because we have new equipment, new experiments that we can design, new numerical tools. We can do very thorough analysis of our data. And in terms of alloy design, we can really explore very complex compositions with new manufacturing methods in a very fast and efficient manner. So that means that we can really synthesize a lot of exotic materials and explore the unknown, right? It's almost like alchemy. We can explore very unknown compositions and discover new alloys and test their performance. So I think that really is a good time to be working in that field for that reason.
This is our last question. What would be the one piece of guidance and or insight you would like to give to future young people, especially young women looking to go into STEM?
So my one advice would be do something crafty overall. If you want to get into material science, it's never too late to start working with the materials that surround you. So if you do something crafty or you do something artistic, like some artistic activity, just find something that you find uplifting and stimulates your creativity. Because as a researcher, regardless of the STEM field you want to go in, creativity really is the key. And so if you start doing that really early, that will develop like a sixth sense within you, and you will develop some intuition about the materials and the matter that surrounds you. In a way, like we could call that street smart, right? Being street smart. So in the area that I work in, there is a strong craftsmanship component or craftswomanship, if we may say. And so you don't have to wait until you're in college and you have to pick a major to start exploring material science. There is a lot of outreach opportunities all around the country, but you can also explore many things at home within safety and guidance. But really, there are many opportunities for you to start developing this intuition about materials. And yeah, the field that I work in is absolutely not reserved to men. We need more women, so that's my final word. Yeah, it's a really exciting time to be working on these materials.
What was something that you expressed your creativity on, maybe as an undergrad, that made you so excited to work on material sciences?
I did an internship in a prototyping service in a company, and that really was my first exposure to material science as a field of study. I had no idea that material science was actually a major before I picked it. And yeah, this internship that's really triggered a passion for material science and in particular metallic materials and composites as well.
Perfect. Well, thank you so much for such a great conversation. It's truly admirable to see a woman so accomplished in your career so early on, especially. You're a great example for future women looking to enter the STEM field. I, alongside EVI, would like to thank you for your time. We greatly appreciate it. We look forward to seeing what comes next from you, and we wish you the best of luck in all your future endeavors and medals.
Thank you so much. Thank you for the invitation.
Thank you all for watching. Please make sure to like and subscribe, as well as click the bell to be notified for our next interview. Our socials are linked here as well as on our website. If you're interested in climate change, renewable energy, biosciences, and all that comes with that, and also looking to see what career path you would like to take if you're interested in that, we highly recommend checking our socials and website out.